Welcome to the next lecture on Illumination Engineering and Electric Utility Services. This is lesson 9 titled Discharge Lamps 2. This is in continuation with the previous lecture on discharge lamps, where we looked at various types of discharge lamps which essentially employ electroluminescence. Now today we continue the discussion further and see what other forms of discharge lamps could be there. We had a look at the mercury vapor lamps and sodium vapor lamps, and we also mentioned that there are neon vapor lamps. One central thing which was there to all these lamps was they had a line spectrum as against the incandescent lamps. So what are the instructional objectives for this lesson? They are ability to list various discharge lamps, state the utilization factor for a discharge lamp. In respect of the utilization factor, we did look at in the last lecture that there is a relationship between the sensitivity of the eye and the radiation ability. We saw that there are certain radiation bands, and when they are closer to the peak sensitivity of the eye, there is a higher utilization, which is the case in case of a sodium vapor lamp, whereas there are two distinct bands as far as mercury vapor goes in the low pressure zone, where the sensitivity of the eye is very low, hardly any utilization, and to some extent it improves when we go in for a high pressure mercury vapor lamps. This is the issue. Now there is one aspect which we say ability of the lamps to reproduce the object color, which is a very important issue when choosing a particular lamp, and that is what we call color rendering. And then the next objective therefore is what is color rendering. And as we said, the mercury vapor lamp had two bands, one in the low pressure zone, the other in the high pressure zone, and in fact we find that the low pressure zone falls in the zone which we call ultraviolet. As recall that the light radiation can be thought of as three distinct regions: ultraviolet, visible and infrared. Now the idea of a fluorescent lamp is to capture or employ the lamp radiating in that zone, and with the help of suitable fluorescent materials re-radiate in the visible zone. This is what is the phenomena of fluorescence. And of course, in doing this, the materials employed to do the process of fluorescence are called phosphors. So the last objective of the lecture therefore would be stating the various types of phosphors that can be used. So continuing with the discharge lamps, we saw sodium lamps having their band spectrum located close to the peak of the peak sensitivity of the eye, are very favorably placed from the utilization point of view, and we say that a sodium vapor lamp therefore is said to be having a high utilization factor. One important thing with all these lamps is that by one of the possible ways of emitting electrons could be electric field assisted emission, could be thermionic emission, that is by heating of the cathode, or by impinging with photons one gets the gas vapor into a conducting mode, and that radiates. That is the issue. So in doing this, we have an arc established, and the arc needs to be maintained, and our color depends on the type of the gas employed or the vapor employed, whereas the intensity of radiation depends on the current level, and therefore there are certain accessories required like starter, ballast, etc. The low pressure mercury vapor lamp has a clear blue line spectrum, whereas when low pressure sodium vapor lamp has clearly a monochrome yellow orange thing. High pressure mercury with certain additives, halides, which are basically they could be bromides, iodides, which improve the spectrum. They make it somewhat continuous and make it a little multi-line. I mean, though not continuous spectrum like an incandescent lamp, it enables us getting some more lines in the visible zone, and especially where the peak sensitivity is there. In fact, if you see in a low pressure mercury, only 25% of energy is converted as compared to a incandescent lamp, but it consumes only about 7 to 11 watts as against. This is considering a equivalent incandescent lamp with a burning for about 5000 hours. That is a very important issue. So, energy consumption, this is, as you can see, it talks about 7 to 11 watts. It is a equivalence between a 40 watt lamp and a low pressure mercury vapor lamp. Now, one looks at employing this. Normally, such lamps are recommended for homes, hotels and restaurants. This gives a warm white color, and it can also be used to obtain blended colors. The blending of colors could be by combination of materials within the envelope or by employing suitable colored glasses. You can, in fact, low pressure sodium lamp is again employed for selective applications like infrared reflections, and these are available with certain oxide coatings inside. Now, we did say, apart from having any of the physical effects producing the radiation, it is the control which essentially ensures good lighting is obtained. In doing this, the accessories play a role. Apart from that, the luminaire or the fixture which controls, and there is a reflector. At times, the envelope itself is used as a reflector, and these low pressure sodium lamps which are employed may often be referred as SOX by some of the manufacturers, can radiate typically 200 lumens per watt of energy consumed, with the lamps available anywhere from 18 to 180 watts. Remember, the way to specify a lamp, all of us are familiar. I go to the market, I say I want a 100 watt lamp. So, if you want to say how we are going to specify a requirement for a lamp, first and foremost is the energy consumption. Next comes the nature of the lamp. These are otherwise sodium vapor lamps are suitable for highways, harbors, marshalling yards. In fact, high pressure mercury lamps are also suitable in such areas, and they are available from 50 watts to 2 kilowatts. They have bluish white line spectrum, and color rendering is bad, and that is where some phosphors are employed to improve the color rendering. In fact, we see, although the mercury vapor lamps can be used in such applications, we are finding that these days most highway application and industrial marshalling yards are essentially with the railway system, railroads, harbors. There are such places also we are tending to replace with sodium vapor lamps, essentially because of high utilization factor which we talked of. The utilization factor talks about, we got that from the sensitivity of the radiation which was obtained by considering the energy radiated from the lamp and the sensitivity of the eye, which multiplied, we find that the line band available for sodium vapor is close to the peak yellow green zone, and that's how characteristic yellowish orange color we find for the sodium vapor. Now, in all these applications, we say color rendering is bad. Color rendering would mean, as the name implies or the word means, is the ability of the human beings to perceive the color in its original sense, and these lamps have very poor color rendering. What we are trying to say is, in case of a mercury vapor lamp, it is possible to improve the color rendering by employing some phosphors. What happens? We saw that there are two zones of radiation. One is in the low wavelength corresponding to ultraviolet, and the other in the midway, and therefore by employing these phosphors we are enabling it to be moved, re-radiated, and in the process we tend to get a band spectrum which is more continuous, and as a result we have a better color rendering. This is the issue. Remember, there were two distinct line bands in case of a mercury vapor. Halides are also added sometimes, we said, and in fact halides were employed even in the incandescent lamps. We have seen that they are iodides of indium, thallium or sodium, and these lamps, in fact these days we have what are called as metal halides. Now, these are basically high energy incandescent lamps which are used for flood lighting, and we do find that there is a risk of blackening of the envelope because of evaporation of the filament, and that's reduced if you have this halides, because they react with the vapor that's available and as a result absorb the heat and they get condensed, and in the process they get redeposited in the filament. Why are we talking about an incandescent lamp in the lecture on discharge lamps? The reason is very simple, because although we have categorized the lamps as incandescent and discharge lamps, in application we find we may go in for a combination of the thing. That is, you have a mercury vapor and an incandescent lamp together in a particular fixture, which can give you, improve your color rendering, at the same time have low energy consumption and give an efficient light system. That's the idea. High pressure sodium vapor lamp has excess of sodium, which saturated vapor of sodium, and sometimes to improve the color, in fact here the mercury and xenon are used as buffer gases, and they are also, remember, all these discharge lamps need a starting gas, which because of low ionization potential, rare gases are used. Here we are talking about xenon being used, and this operates with as good efficiency as 130 lumens per watt with color temperature of the order of 2100 Kelvin. Having said so much, we can look at the properties, various properties of the discharge lamps covered so far, that is the sodium vapor lamp, mercury vapor lamp and the incandescent. We need to compare it with incandescent lamp for one simple reason, that incandescent lamp gives a continuous spectrum which is very close to the natural light. The properties which we are trying to compare, the first and foremost is the light flux, which we said is standardized as lumens. Then the next most important property as far as radiation goes is the efficacy, that is lumen output per watt of the energy consumed. Thirdly, the rating. We said we specify a lamp firstly by the wattage or the energy it consumes. rather than the type. Then comes the thing. Next is the color or the how the radiation has and the rendering of color. Now, the data for the incandescent lamp shows that you can have lamps with as low as 250 lumens to about 40,000 lumens available in the market, with as low as 10 lumens per watt to the highest possible being around 20 lumens per watt of energy consumed, with 25 to 2000 watts, that is 25 watts. We are all familiar, 25 watts we use in our toilets or circulation areas where we need some background illumination but not intense tasks are not performed, to 2 kilowatts. Color radiation is warm white. I said the spectrum is continuous, spreads over the entire visible zone. It is close to the natural light, therefore it is warm white. Hence, we find the color rendering is excellent. So, that is qualitatively saying it is good. In other words, if you see a red color thing, it is truly red. Ballast is what we said is an accessory employed in discharge lamps to essentially maintain the current. Remember, we are operating systems on constant voltage basis, where there is a need to increase the voltage, and once the arc strikes, there is a constant current needs to be maintained independent of small fluctuations in the voltage, and that is possible by having some kind of a reactive circuit in series, and these reactive circuits is what we call ballast, because it boosts the voltage initially for the striking of the arc and then continues to maintain the current. There is no requirement of a ballast in case of a incandescent lamp. There is no starter whatsoever, and we have no run up time, or because there is no arc or anything, it is essentially heating of the filament and that radiates. There is a zero run up time, zero restrike time. Restrike time is what we call, in case the arc quenches, there is a certain minimum time required for the whole process of radiation to begin from ab initio. Let us look at the mercury lamp. Here you have both low pressure and high pressure. See, lumen wise, the low pressure ranges from 450 to about 1200 lumens. It is comparable to what you had in case of a incandescent lamp. So, it is quite possible that with certain additives like halides in the envelope and providing some phosphors, it may be a good idea to get low pressure mercury vapor lamps to give comparable performance. If you look at the high pressure mercury vapor lamps, they have some 2000 to about 125,000 lumens. The efficacy wise, they are comparable both low pressure and high pressure, ranging from 40 to 50 lumens per watt. We have still not reached very high levels, remember that. Ratings could be 9 to 25 watts is the low pressure ones, and 50 to 2 kilowatts is the high pressure one, and color, that is where low pressure is reasonably in the warm white mode. And in fact, some of us are familiar with this milky bulbs which we have been using at home. They fall under this category. In the intermediate range, the light color color is bluish green is the line which is predominant for the mercury thing. We said color rendering is not so good, is okay for low pressure or good, it is not excellent. In case of incandescent, it was excellent. Now, being a discharge lamp, it needs a ballast. We have a ballast which is built in case of a low pressure thing. In a high pressure thing, we have it in the luminaire outside. As such, it does not read a starter, but there is a run up time for high pressure of about 3 minutes with a restrike time, that is in case the arc quenches, it needs about 5 minutes for it to restrike. That is what we are saying. As far as low pressure thing, there is no run up time or restrike time. That is the process. As against this, if you look at the sodium, you see at low pressure itself, the radiation levels are reasonably high lumens ranging from 1800 to about 33,000, and high pressure is from 3.3 thousand to 130,000. That's the kind of a flux that's available with efficacies. That's where the issue is. Very good efficacies, 100 to 183. So for every watt of energy you consume, you are getting a reasonably good light output. That's the issue. And you do have low pressure ones right from 20 watts to 200 watts, and high pressure ones going from 50. Now the light color is something which is to be color rendering is poor, and all of them need a ballast which could be either built in or high separate. It could be a combination of L and C in case of a low pressure one. The starter could be built within the ballast. We do find they have a large run up time. In fact, all of us have seen that the initiating process today, we have run up time close to about 5 minutes. We could see the initiation is through, say, neon gas, which gives rise to a reddish light initially, and subsequently we get the yellowish orange spectrum or light with the sodium vapor. The restrike time in case of low pressure one is about 2 minutes, whereas in a high pressure one it is less than 1 minute. Now, having said this, we take up what are called as fluorescent lamps. Now, fluorescent lamps, as the name suggests, employ fluorescence, but they are still the discharge lamps themselves. Recall that the mercury vapor has two separate distinct bands, one in the UV region, the other in the visible region. Now, the fluorescent lamp essentially takes care of converting that radiation available in the low wavelength or the UV region into visible zone by the process of fluorescence. Let us see. If you have a luminescent powder provided in the tubular vapor lamps, it in fact improves brilliancy of light. That is what we found for the mercury vapor lamps, we did mention. So, what we do is take a low pressure mercury vapor lamp, consider whose radiation is predominantly in ultraviolet region. It is allowed to impinge on luminescent materials. As a result, it re-radiates at longer wavelengths of visible spectrum. This we had defined right in the beginning as one of the processes used in the artificial lighting to produce radiation. This is absorbing the light at one wavelength and re-radiating in the visible spectrum. That is what we are doing. So, this is the process of fluorescence. So, you have a glass tube with a small drop of mercury and small amount of argon. Again, why argon? Argon is necessary to vaporize your mercury to initiate the arc, because it still is a arc lamp or a discharge lamp. Now, the whole process is such that we control the pressure, voltage and current, so that we have in the 253.7 nanometer line, okay, and then radiate at longer wavelength. A typical 40 watt fluorescent lamp will use about 2 to 3 grams of phosphors. We will see what these phosphors are. Phosphors are nothing but these luminescent powders which we are talking about being coated within the envelope of the discharge tube. We will have a look at the various material that can be used. A small amount, see the amount required. 40 watt lamps are very commonly used, this which all of us have been using in all our offices and homes. It is very commonly used, and we find that the maximum sensitivity of these. Now, with respect to these phosphors, one talks of sensitivity. Sensitivity means the point on the wave spectrum where they absorb the light and then they re-radiate, of course, the zone. Keeping this in mind, fluorescent lamps are available with different nomenclature. The first one is daylight fluorescent lamps. In fact, the idea is they are supposed to be having color temperature corresponding to average noonday light, hence they are called daylight fluorescent lamps. Remember, this is no longer a mercury vapor lamp in the earlier form. It's though initial radiation is obtained by electroluminescence, it is the fluorescence which is giving you the ultimate output, and hence it is giving a different kind of spectrum. It is, you cannot say it's anymore what you call line spectrum. Now, this is okay where the demands are not very exacting. As against this, we have a standard white light. In fact, most of us are using standard white light lamps very commonly, which has a color temperature of 3500 degree. This is employed for general lighting. Then there is a lamp which has a color temperature between a standard white light and daylight lamp, which is around 4500 degree. In fact, it is called 4500K white lamp. And you do have, where the illumination levels are required are less, are having soft white lamps. This gives a slightly pinkish because the output itself is 25% lower than the standard lamp, and this is used where dim lighting is required. The application could be circulation areas in a residences, the corridor connecting the various bedrooms, circulation areas in a restaurant, in a hotel, where hotel, oftentimes we have observed that hotels we tend to have dim lighting. The one advantage of that is you get the privacy you need. It's a public place where many people are eating, so you would like to have a private environment for the people with your colleagues or family. So now, on what factors does this depend? This depends on the dimension and voltage. The factors that come out are luminous efficacy is a very important thing. You have brightness, lumen output is a, in fact, very important thing. Lumen maintenance is another issue which we oftentimes in analyzing or calculating take it in terms of the maintenance factor, because lumen output with age reduces. Now, for reliable starting, we use preheated cathodes or hot cathodes. There are two categories. Preheated is prior to the arc discharge, it gets heated. Hot cathodes is continuously. Now, the issue is, we have already said, although discharge lamps are radiating mostly by arc, they have two electrodes at the either end, which depending on the cycle of the AC sine wave, each of them acts as cathode, and hence each cathode is in turn heated by a filament which is similar to your incandescent lamp. Now, here what is done is, if you have a certain open circuit voltage, we rate it such that the discharge occurs by using half the open circuit voltage. That is, our lamps operate on 230 volts, so we expect around 110-120 volts to be the drop across the arc, and the rest of the thing by the ballast. Ballast, you know, ballast is required, one, to boost the voltage across the two electrodes so that there is a discharge. Lamp voltage, of course, depends on the arc length, bulb diameter, lamp current. The hot cathode obviously can operate at lower voltages than the cold cathode. Cold cathodes, the basic disadvantage, we did mention this, cold cathode would mean The emission is essentially through electron emission and can have drops of the order of 70 to 100 volts at the cathode itself. This diagram shows the complete functioning. We have all the accessories shown. There is a glass envelope, it is a long tube with the lamp. At either end there are two electrodes which are basically similar to your what we found in the sodium vapor lamp or mercury vapor lamp. It shows the complete circuit diagram. This is the total line voltage applied across that ballast or choke, which is known as, which is predominantly electromagnetic. Of late we have been using electronic chokes, which we will take up in a later lecture on control devices for illumination system. We will look into the electronic ballast during that, but suffice it to say, in the circuit sense, it is an inductance which helps in boosting the voltage initially to strike the arc and later on to be able to control the. There is a capacitor which in fact, because of this inductor, it's bound to alter the power factor, and we know that all our systems should operate as close as possible to unity, so that the conductor sizing for the input power supply becomes nominal. And there is a switch. In fact, initially the current flows through the choke, the left electrode, and through that bimetallic switch, which is also known as a glow switch, to the other electrode, and thereby heats the two cathodes, two electrodes at each end, and creates the vaporization. And since it is a bimetallic switch, to the passage of the current, it heats, and there is a differential expansion between the two metallic elements, and the switch opens, and as a result there is a transient created. Remember, if you have a RL circuit and you open, there is a transient, current transient, and that builds a very large voltage across the two electrodes and thereby strikes the arc. Once the arc is struck, the inductance is in circuit and the switch is out of circuit, and therefore at that time the capacitor comes into the circuit to ensure that the power factor is maintained. And as we said, normally we try to have at least the arc drop, voltage drop across the lamp, that is only the arc tube, to the open circuit voltage, total voltage the supply, at least 2. But this we have seen when we switch on, there is some amount of flickering. That is because at times the required voltage may not build up, or even if it has built up, there is insufficient vaporization and the arc does not get established. So you do find that it may take few cycles. That is why we can see the flickering of the lamp prior to it glows. So in order to have instant start, the design is done in such a way that this ratio is kept around 4, and then the lamps are called instant start. Here I must mention that these days, in fact, these lamps are available in more compact form with as low wattage as 18 watts or even lower, and they are termed compact fluorescent lamps. Imagine having a glass envelope in which there is an arc tube along with its ballast, starter, and power factor correction capacitor completely within this. So these are termed the compact fluorescent lamps, and the beauty is that they are possible to be mounted in the conventional fixtures meant for the incandescent lamps. Now, having looked at this, the one important issue is the material of the phosphor, and we said phosphors are coated on the interior of the envelope. They absorb the light radiated in the UV region, So, there is a certain sensitivity of these phosphors, they respond to a particular radiation, and having responded they have a ability of radiating over a certain spectrum. This spectrum is what we want it to be in the visible zone. Now, let us look at the picture which shows three different materials. The first curve shows has a peak sensitivity around 253.7 nanometer line, which is a zinc beryllium silicate. Okay. Now, as against this, we do have magnesium tungstate, which is having a peak around 260 between 265 to 280, and the average sulphide which is normally used, the sulphides are very often used, these are special materials, zinc beryllium silicate and magnesium tungstate. The average sulphide has around 5.4 nanometer line. Now, in fact, the health purposes we do use this light, and it's called as a black light in that zone, because if you don't make it visible by. So, let us look at the some of the chemicals that are employed, fluorescent chemicals, we call them as phosphors. So, we have phosphors versus the color, okay, calcium tungstate. Then you talk of the color, it is basically what we are trying to say is in the radiation spectrum where it is going to be maximum. Calcium tungstate can be after it goes into fluorescence may be termed to be blue, magnesium tungstate will be blue white, zinc silicate is a green. Green is good because it is the peak sensitivity of the eye, yellow green. Zinc beryllium silicate is yellow white, maybe we look for that. Cadmium silicate is yellow pink, cadmium borate, all these materials have been used pink. This is the color wise. Now, this is the range over which it can be excited. This is the range of excitation would mean if the UV radiation is available, this phosphor will respond and go into fluorescence. You could see the calcium tungstate is around 220 to 300, whereas magnesium tungstate is around 220 to 320 and zinc silicate is around 220 to 296. Going further, zinc beryllium silicate is around 220 to 300. It has to be that way because it's below 300 is when we have the cadmium silicate around 220 to 300, cadmium borate 220 to 360. Then the next issue which comes is what is its peak sensitivity. We saw in that figure response curve there is a certain wavelength at which there is a peak response or the fluorescence is a maximum. The calcium tungstate is known to have peak around 272 nanometers, whereas magnesium tungstate around 285 and zinc silicate around 253.7 and zinc beryllium silicate around 253.7, cadmium silicate around 240 and cadmium borate around 250. Continuing with the characteristics of this chemical, the range of emission, this is also equally important. After having absorbed the light, after going into fluorescence, what spectrum does it emit? That is a very important. You see calcium tungstate is around 310 to 700, which means it is covering the entire spectrum of visible zone. Magnesium tungstate is around 360 to 720, whereas zinc silicate is only between 460 to 640. That is a important issue to be kept in mind. Zinc beryllium silicate is around 480 to 750, whereas cadmium silicate is, as you see, as we are going along down the table, it is shifting a bit to the right. That is a very important thing to be kept in mind. Emitted range, cadmium borate is between 520 to 750. Now, notwithstanding this, Okay, it's got a range, but what is it that matters? It again matters that the radiation re-radiated after fluorescence, where does it have peak? How does it compare with the sensitivity of the eye? Where is our eye sensitivity maximum? It's around 550 nanometers. So that's the ultimate thing which is going to decide the efficacy of the phosphor and usability of the phosphor. So you have to work towards creating the discharge around the sensitivity of these phosphor from the point of view of going into fluorescence. Next, look at the emitted range and see where the emitted peak is. If you look at the emitted peak, calcium tungstate, though we saw that as we go down the table there is a shift towards the right in the spectrum, but there is also a shift to the right towards the peak emitted peak. That is very important. I look for in the close to the peak sensitivity of the human eye. Calcium tungstate has around 440, magnesium tungstate has around 480, zinc silicate around 525, and you find zinc beryllium silicate 595, cadmium silicate at 595, cadmium borate at 615. So what do we see? If you look at the ultimately, and you will find probably zinc silicate and zinc beryllium silicate, these are possibly the most commonly used phosphors are suitable, because from the point of view of your high what you call emitted peak sensitivity close to your listing. So what we have looked at is that we do find as a whole there are two categories of discharge lamps that are possible. One, you have a discharge, arc discharge, and essentially work on the principle of electroluminescence, and the band that is obtained is a line band, and we have seen the normal gases that are employed are neon, mercury or sodium. Now right in the beginning we said it is necessary that we have good efficacy. Efficacy of a lamp is talked in terms of the lumen output per watt consumed, and it is amply clear from the data observed that sodium vapor lamp scores over all other lamps from the point of view of luminous efficacy. However, what did we find? We found that it has a very poor color rendering. Oftentimes color rendering is not essential in areas like harbors, industrial establishments, and probably on highways and streets, and that is the reason why in those areas one could employ these lamps. However, interior work calls for application of good color rendering is required. Color rendering by definition we said is ability of perceiving the color in its normal thing. Now the next thing is use of fluorescence. Fluorescence was trying to extrapolate or take the radiation at one frequency and absorb and re-radiate. And what do? We use mercury vapor for this, because we find the mercury vapor has two bands, one in the ultraviolet zone, the other in the visible zone. We are trying to employ or use that region that is available in the ultraviolet region, and this is done using fluorescence. Fluorescence calls for use of certain phosphors. When we talk of phosphors, three parameters become very important. The one, the sensitivity range, that is the range of radiation when it impinges sends the phosphor into fluorescence. 2 is the peak of this, that is very important. So, because you are having a line spectrum, we design to have that line available so that the particular phosphor gets excited well. After having got excited, it is the emission that is important. Emission again has a range, and fluorescence looks for emission in the visible zone, and we saw among the materials that were used, zinc silicate and zinc beryllium silicate was having sensitive emission peaks close to the peak of the human eye sensitivity. That is what we had a look. Now, all these being discharge lamps, they are depending on the arc discharge, and arc discharge calls for striking a arc between the two electrodes with the gas or vapor there, and therefore, we have accessories associated with that. We had a look at that. We have seen that different lamps have different startup times and different restrike times. So, that is the thing. So, one could say that in the low pressure sodium vapor lamp, sometimes we do use the indium oxide or halides are coated, and that act as reflectors. That is one thing. High pressure sodium mercury vapor gives bluish white line spectrum, and sometimes in order to get good color rendering, here again I must reiterate that color rendering was little better than sodium vapor as far as mercury vapor goes, and therefore, if energy is the issue or the power consumption is the issue, one could replace the incandescent lamp by a mercury vapor lamp, because mercury vapor lamp does have what you call higher efficacy compared to the incandescent lamp. If some luminescent powder is put in the tubular lamp, it enhances the brilliancy of light. That is what we have seen. This is essentially considering a, what does it do? This powder is nothing but the phosphor that is converting the UV radiation into visible zone. This essentially is doing that. Radiation from low pressure mercury vapor lamp is allowed to radiate at longer wavelengths. We have seen extensively how phosphors react. They have a peak sensitivity, there is a sensitivity band, emission peak and emission band. Keeping all this in mind, we found some of the phosphors that are used. Now, with this in mind, the fluorescent lamps which are quite often used, that is what in fact we have enabled by going into fluorescent lamps, utilization of mercury vapor discharge, which had a low utilization factor when used otherwise compared to sodium vapor, but good color rendering, and that is how they have been in stay as far as the interior lighting goes. And they are categorized as daylight lamp, which has color temperature close to noon temperature, noon sunlight, standard white light and soft white lamp, and the various ways of fluorescent lamp dimensions. Of course, there are two major dimensions, one is the length, other is the diameter. We will look into some of these issues in the next lecture, where we will also have a look how every watt of energy that goes in gets distributed in various forms. So, it depends on the lumen maintenance and starting, the reliability of starting, that is very important. Now, starting depends on the, as we saw, the voltage across the discharge tube and the total voltage, that is the ratio which we termed as the open circuit voltage to the lamp voltage. In fact, we saw that this has to be around 4 to have a instant start lamp. Lamp voltage, of course, we said bulb diameter, current and arc length decide. So, we are familiar with 1 inch dia tubes, and we are also familiar with half inch dia and quarter inch dia, which are coming these days called energy savers. Okay. You remember that it is a discharge and the diameter has its own impact. Having said this, some of the questions that may be answered here: halide lamps, we have seen what halide lamps are, what kind of halides are used, why are mercury vapor lamps preferred than sodium lamps, describe the working principle of a fluorescent lamp. For what wavelength do we get maximum efficiency for a fluorescent lamp? How do we obtain reliable starting of a fluorescent lamp? What are the voltage drop at the electrodes and the choke for a fluorescent? This is where it addresses basically the ratios that need to be maintained. Some of the answers to questions which we have already asked in a previous lecture on discharged lamps. What are the different electron emission methods? What method is employed for mercury vapor and sodium vapor lamp? The different methods are electric field emission, thermionic emission and photoelectric emission. As already told, electric field emission is by application of high field, thermionic is preheated and photoelectric is the by impinging. In mercury vapor lamp, electric field emission, and sodium vapor lamp, thermionic emission is often used. That is, normally low pressure mercury vapor lamps do not have any heated cathode. What are the commonly used gases in discharge lamps? Commonly used gases are sodium vapor, mercury vapor, neon and argon. Neon signs are often employed for display purposes. Signboards, we have seen many in the shopping malls, and it's quite often used, characteristic red, and of course other colors are obtained by a combination of gases or combination of envelopes. What are the disadvantages of using a cold cathode lamps? Cold cathodes, what are cold cathodes? Cold cathodes are those which employ field assisted emission, and cold cathode lamps consume a lot of energy and there is a large voltage drop, that is the consumption of the cathode, therefore decreased. It also leads to what we call disintegration of the cathode. What do you mean by run up time? We have come across this run up time because the process after applying the voltage, there is a certain finite time for the discharge to take place and the arc to be established. The time taken for the starting gas in the discharge lamp to initiate discharge process and transferring to the main gas, this is what we call run up time. So, this is, we have seen, in fact the run up time used to be very large for the lamps in the initial phase, and these days we have fast run up or less than 5 minutes. In fact, we have studied that sodium and mercury vapor lamps did have large run up time of 20 minutes etc. These days we have them within 5 minutes. Why do we connect a choke or a ballast in series with a mercury vapor lamp? It enables high potential build-up, that is what we said. Arc needs a high voltage development that is done at the cathode while starting and limits the current thereafter. This is possible because we know that if there is a inductive circuit, RL circuit, you break or you create interruption in that current, that builds a voltage transient, and that helps the arc to build up. What steps are taken to improve the low power factor of mercury vapor lamps? In fact, generally mercury vapor lamps low power factor. So, why mercury vapor lamps, even sodium lamps, we can, wherever there is power factor correction required, we have an inbuilt capacitor. In fact, we have seen the starter, cylindrical starter provided with the fluorescent lamps has this. What do you mean by principal line? What is the principal line for mercury vapor lamps? It is the wavelength of the lamp output spectrum which gives the maximum light output. For mercury vapor lamp, it is around 365 nanometers. This is the thing. Thank you.